Okay.
So I guess we can start. Are you okay to start, Antoine?
Yeah.
Okay, so I'll just introduce you. Thanks everyone for coming. Thank you, Antoine, for giving the talk. Today we have a talk by Antoine Vuignier, who is going to talk to us about gravity from a matrix integral. Thank you very much, and please take it away.
Hi, everyone. Thanks, Bruno. Thanks for the invitation. So I'm going to talk about this work that actually those two works that okay, it's one work that we split it in two. In those two papers that we did with my advisor, Juan, and also Shota from CERN. Adrien is a PhD student also with Juan, and Xiong was a postdoc with us at the EPFL, but now he's in Saclay. The broad picture, like the big picture of this work, is how to use the gauge gravity duality to understand the emergence of space-time in quantum gravity. And that will be my introduction. And then to be very specific, I will study one model, the AKKT matrix integral, and in particular the mass deformed version, which takes place in the gauge side of the duality. And then in the second part, I will discuss the geometries that live in the gravity side. So let me start with the big picture. So how do we understand quantum gravity? At least is one way to understand it that I will use today. So we know gauge theories. So as usual quantum field theories, there are spin one gauge fields. Typically, there's the standard model where those gauge fields are the forces, the electromagnetic strong, weak. It's one point here, that box, it's supposed to be all the gauge theories we know. You typically have matter fields that are spin-half fermions, or you can have both subscalar fields, whatever. But you have no spin 2, so you don't have. I don't put gravity with quantized gravitons in that box now. There's one corner that is a bit special. So here I drew a corner. I don't know the size of it. I don't know how to characterize it. We just know some examples. So there is some special gauge theories, and those ones you can take a limit where n typically is the dimension of the gauge group and lambda some coupling of the theory. Where they go to infinity, you get general relativity as described by Einstein's equations. But this limit, I think it's better to think of it as h bar goes to 0. It's really the classical limit of this quantum theory. And the classical theory is this. So how do you call a theory that is quantum? It obeys all the axioms of quantum mechanics. And the classical limit is general relativity. This, I think it's quite conservative to call those gauge theories theories of quantum gravity. And we know a few examples that come usually from string theory, but we don't really know how to characterize that corner. And it will be the big goal to really understand this, because if you understand what is special about the gauge theories that live here, then maybe we can start to do some model building and try to apply these tools to study gravity in the real world. Okay, so this is what's called the gauge gravity duality, and sometimes we call this also holography, because these gauge theories, it lives in some dimensions. It can be 4, 3, 2, 1, even 0, and the gravity can be 10 or 11 or 9. Usually it's high dimensions, or 5. But those dimensions, they don't have to agree. So this is why sometimes we say the gravity part is a hologram of the quantum theory. Let's maybe a bit more specific. So about what we're trying to do. Suppose you don't know quantum mechanics, but you know linear algebra, and someone arrives and gives you the Hamiltonian, and he tells you how those operators act, and they say, "Ah, that's a pendulum." But then, do you trust him? I mean, how do you get a real classical pendulum and the first quantum fluctuations from this? Of course, if you've taken quantum mechanics, you can create coherent states. And those states, if you plot the wave function, you will see that it can be really peaked around the classical solution, and it oscillates at the classical frequency. So there you have back your classical pendulum. But those coherent states, we don't know how to build them in the picture I had before. So the most famous example of this gauge gravity duality is the ADS-CFT correspondence, where the CFT side is the gauge side, and we don't know how to create coherent states in n equals 4 super-Young mills that are the type 2b spacetime. But that will be important to understand how to do it, to really see explicitly how the spacetime emerges. Let me present some models to be really explicit. So this is one model I like. It's not going to be the model I will discuss today, but it's quite similar. It's called the BMN model. So here I write the Hamiltonian is quantum mechanics, usual quantum mechanics. But the degrees of freedom are packed into matrices. So those x's, they are n by n matrices. Each entry is a boson of so you have n square bosons. Those p's are canonical, the conjugated momenta to those bosons. So each entry in the p matrix is conjugated to the corresponding entry in the x matrix. And then we also have fermions that are also n by n matrix. You take a trace, you have a Hamiltonian. If you expand this, it's usual quantum mechanics. And okay, you have some mass terms and some interactions. And what I want to argue is that, okay, this Hamiltonian, it might look complicated, but it should be intuitively simple because, right, if G is 0, then all those terms vanish. You just get P squared and some mass terms. So it's just harmonic oscillators. So we have those n square harmonic oscillators. We turn on some interactions. So here you have very specific interactions with those commutators, those fermions, this x cubed term. And you take those interactions to infinity, we expect some gravitational description. How does that happen? What is special about those interactions such that those harmonic oscillators become gravity? So this is one question we wanted to address. But even quantum mechanics, when you do strong coupling, it's very hard. And it was difficult to make progress. So is there a model that is similar to this, but that will be even simpler? Well, there is. It's the one we'll talk about today. It's the polarized AKKT model. Here it's not quantum mechanics, it's more like statistical mechanics because there's an action. So no, you don't have by the full action, there's no integral over time. The matrices are time independent, just n by n matrices. You again have x's and some fermions that are n by n. And it's a bit similar. No, there is this omega. When omega is 0, you can solve the model, and then there should be some gravity dual. But this is a nice picture because if you think of this as a gas in statistical mechanics, those interactions are special. So it's a special gas, and at strong coupling there is an effective description of that gas that is general relativity. And so what is special about this? So I will not answer those questions today, unfortunately, but it will be maybe for a future. But for today, we will study this model, so this AKKT model, and I will argue that this integral has saddle points where the matrices take some specific values. Those J's, there are irreducible representations of SU2. So this X is like a representation of SU2 decomposed into E-reps. And so the right side I will explain later, but basically those rho and z will be coordinates in some space-time. You have to attach 2 spheres and 6 spheres with different radii. And the point is that if you know, right, those x's, so the saddle points that are characterized by those numbers, and big n's are the dimensions of the E-reps, small n's are the multiplicities. So here the E-rep with dimension big n1 appears small n1 times. So if you know those n's, you know those z and q's, and I will explain the z and q's, they completely determine the geometry. So there is a one-to-one correspondence. Okay, so that was my motivation. I will discuss the AKKT model more in details. So I don't know if you have questions about the big picture, or maybe you can ask now. Okay, let's continue. Here, okay, those eigenvalues, there should be some effective description of those eigenvalues that is geometrical. So let's talk about the AKKT matrix integral. Let me start by first the undeformed version, so it's the one that was originally proposed. So that's an integral over those matrices xi. You have 10 matrices and 16 fermions. And this action, you only have the commutator and these interactions between fermions and bosons, such that it's supersymmetric. So why do we have supersymmetry? Because that usually makes the model super easy. Because otherwise, it's very hard to solve them. So with this extra symmetry, it's important to first solve that case, which is the easiest, and then try to reduce it and eventually at some point to have no supersymmetry at all. There is also then global symmetry because those xi you can rotate. Right, it's a SO10 index. There is a UN symmetry that we call gauge, but here it's not really gauge symmetry, right? Because it just matrices UN. It just means you can change the basis of those matrices, and because we take a trace, the action is invariant. But usually gauge symmetry, it's dependent on the point in space-time. Here, there's no space, there's no time. It's a 0 plus 0 dimensional quantum theory, if you want. So we just call it gauge because in the higher dimensional case, where we have similar forms for actions, it corresponds to a gauge symmetry. But this model, it's a bit too simple. So there is no complete constant. There is only n, the size of the matrix. It's the only parameter. Actually, this partition function, we know exactly what it is. There is a formula. It's like some function that depends on n, and we can write this down explicitly. And people try to do holography with that, but it was a bit hard because right, usually we want to have some coupling that we can tune and export different regimes. Here there's only n, so it was a bit unclear what to do, and we're a bit stuck. So it's better to study this polarized version where we add a deformation. So the deformation has two mass terms for the bosons. We break the matrices into three. Small I goes from 1 to 3, and P goes from 4 to 10. So SO10 is broken to SO3 cross SO7. The XIs have special interactions between them with this Levi-Civita symbol. And then there's a mass term for fermions, like psi dagger psi or something like this. This deformation, it preserves all the supersymmetries. So it's not the same supersymmetries of the original model. You have to deform the supersymmetries as well. But there are still 16. And now we have this extra parameter omega that we can tune and study when omega goes to 0, omega goes to infinity. So because it's the mass, when omega goes to infinity, it will be simpler with its infinite mass. So the saddle contribution is exact. But actually the coupling constant is more like 1 over omega. So the gravity limit should be omega goes to 0. What can we do with this integral? We can study its saddles first. So in a higher dimensional QFT, we'll call that the classical VQA. So you take this bosonic potential because all the fermions are set to 0, and you study the configurations of matrices such that you have an extrema of that function V. So what you find is that XP's, so those P's need to be set to 0, and those I's, because they have this additional term, they need to satisfy this equation. So this is just the defining equation for an SU2 representation, which is why the most general form of all those VQI is to write Xi as this SU2 representation, which is a block diagonal into a reps. So again, those J's, I ends are those big ends are the dimensions of the arrays, and we have small n's copies of each. But because the matrix is n by n, we have this constraint that big N is equal to that sum of what you sum the dimension of each multiplied by the multiplicity. And this is one way to express the partition of n's. So this allows to count how many of those VQA there are. There are as many VQA as there are partitions of n. They are non-equivalent. So if you evaluate the potential on those VQA, you get something that depends on the special VQA. So you see that the ones So the irreducible ones, so the one that have ns which is equal to n, is when xi is an irrep, the n by n irrep of SU2, then this potential is maximized and actually minimized because there's a minus. And so it's the leading saddles and all the other saddles are subleading. This is when omega is large. When omega is small, they can all contribute. So it's a good first look into the model, but it's not really enough to write exactly the partition function and study it for all values of omega. For this, we did it and we used supersymmetric localization. So here we'll explain how to complete this partition function. So the big idea is if you have the partition function z, you can define a new partition function zt that is the original one with this deformation minus t delta v. Here I'm not saying what delta v is yet, but if you can find a delta v such that the time derivative of that z is 0, then the t derivative, then it's independent of t, and you can take t is infinity, and that will make the saddle point approximation exact. So you just have to do a saddle point analysis with the one loop determinant, and you compute this integral. The thing is, most of the time it's unclear how to find such a function delta v, but with supersymmetry we can choose delta v to be the supersymmetry variation of some fermions like this. And it has a property that delta squared v is 0, and the time derivative is equivalent to taking another, I want to say that if delta squared v is 0, then the t derivative is 0, and that will be satisfied. So for this, you just want a v such that delta square is 0, and so you choose v is delta of something, and that's something you can choose. And the standard choice in this supersymmetric localization is to take this fermion term, like psi transpose delta psi, or delta is this transformation here. So you do this, and then you can take the limit is infinity. I will not discuss too much those details because I don't think it's good for a talk. It's in the papers. I'm happy to discuss if you want to understand those at some point, but I will just quote the result. So you do this localization and you find saddle points where the xi's here is the same as before. I've wrote a bit differently. So you have those j's, and so right, n times is like tensors with the unit matrix of size small n1 by small n1. And then the xp's are also 0 except x10. No, that's the difference. That takes this form. So it's like there are matrices that live in the other side of the tensor product here. And using the UN gauge symmetry, you can diagonalize them, and you remain with those numbers, like those m, i's, s. And the full integral, there was an integral over all the matrices, and using this localization, you only have an integral over those m's. And that's the result. So the full partition function takes a sum. So this curly r, it means an irrep. So it's a sum over all the saddles. Each saddle is an irrep of SU2. Sorry, a representation that is like a sum over the partitions of n, if you want how to decompose the representation of SU2 into irreps. There is some prefactor, then there is this integral over those m's. The one loop determinant is given by this funny function. So this is a product over all s. So the s and t's are labels that goes along the irreps into the representation r, and I and j are the multiplicities. And there is this function f of x that takes this form. So okay, so far the physics is a bit unclear, but we'll see a good analogy soon. Here there is still this integral over m, but you see that here the integrand also scales with those n's. So you can take a large n limit, and I mean, that's the exact result, but for gravity, we're interested in the large n regime. So if you take the large n limit of this, you can do a second saddle point, right? First it was the supersymmetric saddle point that was exact that gave this formula. Now I do a second saddle point analysis in the large n limit. And what will be important is the equations that, right, if you solve for the saddle point, you find some equation that has to be satisfied by those m's. So when n is large, I agree this small ns is large also, it's good to approximate, right, all those m's that are the eigenvalues of the matrices. We describe them by the density of eigenvalues rho, and this is what appears in that formula. It will come back later. But no, it's good to interpret this as statistical mechanics because it just, so far, just some formulas that's a bit unclear what it means. So if we think of this eigenvalue density is a particle density, then you can derive the saddle point equation from this effective action. So it's like saying z, the partition function is e to the minus s effective, or that's the formula for s effective. And so you have some background terms, some right here it's constant, then you have rho with some background term x squared. Then there is a two-body interactions that comes from this k. So k was that function before is like the large n limit of this f. And here this mu is the Lagrange multiplier that appears because the density is normalized to n, there are n particles. So that's an action, that's the effective action for this gas. So it's a gas with two-body interactions, and somehow the effective, this should be equivalent to gravity in some regime. If we look at those interactions, so this function kst that appears here, the two-body interactions, we see, so here's the formula that is something, but if you plot it, it's a bit more clear. So SNT, as I said, it's between the E-reps. So if you have the eigenvalues in the same E-rep, it's these blue lines here. So you see, it's always the same thing. It's the same qualitative behavior for all of them. It's just for the blue one, you have a divergence at x is equal to 0 because it's in the same. And then those interactions, they are attractive at long distance, but repulsive at very short distance. So you can form bound states. You actually have those particles, and there you have this gas, and it attracts. And if they get too close together, then they repel. So you have bound states there. And we'll see how to interpret this with gravity a bit later. Do you have questions about this gauge sign? I will describe a bit more the gravity. Okay, so let's see the geometries that are associated to that model. I will do a brief review. So these geometries, they are geometries in type 2b supergravity. So let me just explain what this funny name means. So this is just GR, and you have some matter fields. So you have the axion and dilatance that are two scalar fields. So this phi and that chi, they are scalar fields minimally coupled to that metric G. And then there are two free forms, F3 and H3, that are called the Ramond-Ramond and the Neveu-Schwarz forms. They're like electric fields. If you do Einstein-Maxwell, you would write a two-form F2. Here it's a bit okay. It's a three-form, not a two-form, but it's a bit the same. You have gauge fields, and you have objects that are charged under those gauge fields, and they have charge. Blah blah blah. In addition, we also have some fermions, the gravitino psi mu and dilatino lambda. I'm not writing the action because for classical solution, it does not, they're always set to 0, so I'm not saying how it couples here. But the fact that there is those fermions is important for supersymmetry. And what is supersymmetry in here? It means that you have, some solutions. So some solutions of those fields equations that have killing spinors. So there are spinors, epsilons, that satisfies those equations. D mu epsilon is 0, delta epsilon is 0, where d mu is the covariant derivative plus some terms that depend on the matter fields here. And delta is also something similar with those matter fields here. It's not too important what they are. What it means is that if you want to have such solutions, you cannot have it for generic arbitrary values of those Bose fields. It will put constraints between them. So for example, you'll have phi and chi that will be related in some way. And the point is, when here we will have 16 supersymmetries, so all these solutions, all those fields will only be dependent on only one function, and that comes from the existence of such killing spinors. That's for the idea. But now, so we want geometries. We have to guess a bit. What are the geometries that can be dual to the polarized like AKT? So someone that knows string theory might tell you that you should look at things in type 2b supergravity. That comes, I will tell a bit more later why that is the case. But let's say you know this, then you want to match the symmetry. So you want something that is SO3 cross SO7 symmetric and has 16 supersymmetries. So you write a metric that has an S2 and an S6 to have this SO3 cross SO7, and then it's in 10 dimensions, so you need 2 more coordinates. And you have some functions here that can depend on those coordinates. And you solve for the killing spinors. And you do this analysis. We didn't have to do it because there was the group at UCLA, they did it for SO3 cross SO5,2. They did a Lorentzian case, where here instead of the 6 sphere, you have ADS. So we could just take the result, which did a bit. We took the result and we analytic continued, and it gives a solution in Euclidean. And it turns out that those functions R2, R6, and H, they only depend on a single function V, because of those killing spinors, it was the point, that satisfies this equation. So this maybe you recognize as the Laplace's equation, but it's in 4 dimensions. So if you have axial symmetry, so this part with rho is the Laplacian for something that is spherically symmetric in 3D. But in addition, you have this z, so it's like a cylinder where z is the coordinate along the axis of the cylinder, and rho is the radial coordinate. But it's 4-dimensional, so it's a good trick to, instead of thinking about this complicated geometry, we can think of this electrostatic system such that V is the solution. Okay, here I just want to be very explicit about all this supergravity thing. You see, everything depends on V. Dot means a derivative with respect to rho. Prime means a derivative with respect to Z. So that's the metric. So here's like the H I was writing, the R6, blah, blah, blah. You have also dilaton axion, 3 forms. This delta is just to simplify a bit the notation. So you see, if you know V, if you solve for V, you can plot all those functions. Now let me describe this electrostatic problem a bit more. So here you see, if you take any V, you will have some problems because, for example, this V prime prime of V dot, that should be positive because the metric, each coefficient should be positive. And this will translate into boundary conditions for the electrostatic system, which is good because electrostatics, the solution is only fixed once you have boundary conditions. So more specifically, if you study this, so there was a paper by Maldacena and Lin where they did something similar for 2A geometries. So they also have this electrostatic potential. It was in 3D, and they did a similar analysis, so it was easy to follow and to translate. So what you need is the boundary condition at infinity. So you want everything to be positive. You see that you need to add a background potential that grows at infinity. And because it's harmonic, you can choose between all the harmonic polynomials, and it turns out that this one will have good properties once you examine the solution you get. You also need a conducting plane at z is equal to 0. And then you can have an arbitrary number of finite size disks that are centered on the z-axis. So those disks, they are conductors, which means that the tangent component of the electric field, so the raw derivative of the potential, is 0 on those blue lines. And if you see what that means for the metric, it means that the coefficient of the two sphere vanishes. And on this axis, you see that the coefficient of the sixth sphere vanishes. And that means the geometry has some non-trivial properties. So if you draw a line, this gray line here between two of those disks, and you attach an S2, so it goes from a point where S2 is 0 to a point where S2 is 0, but in the middle, it is non-zero. You get some closed three-dimensional manifold. It's like if you put an S1, right, this is like the axis of the Earth, and here we have the North Pole, the S1 is 0, the South Pole, it's also 0, and in the middle, it's non-zero. So it's a two-sphere. Here is similar, but you get something three-dimensional. And similarly, if you go around a disk from the axis to the axis, you get something as 7, and you attach the S6, you get a 7-dimensional manifold that is also closed. And yeah, that will be important to later. So those are the geometries. Now you have this electrostatic system. You can put the disks as you want. You choose. I didn't say, but the size of the disks, it's fixed, because right, those disks, they're like, here it's like a tip is like a point, and usually when you have conductors at the tip like this, the electric field is infinite. But because you have this background potential, so first, if the electric field is infinite, then it's bad because the geometry will be singular at that point, and we want something that is not singular. But because there is this background potential, you have an electric field that pushes inside the disk from this background component, and the disk has some charge, so it pushes outward. So if you tune the size of that disk, if you know its charge and you know where it is, so you know how the background potential acts, you can choose the size such that the electric field vanishes at the tip. And if you do this, then the geometry is completely irregular everywhere you can go. It's regular on the disk, it's regular close to the axis, nothing diverges, it's fine. To get some intuition, we can look at the metric asymptotically, because usually those metrics in dual geometries, they correspond to the back direction of something in some background. So here we try to identify what is the background by looking at that infinity. So we can use this electrostatics because we know the disk, so we expand with multiples. So this P is Q times the distance, right? There is a conducting plane at 0, so you put images, and then you compute the dipole, and you write the potential like this. You expand at large distance for the metric and all the things, and you find that the metric is actually flat. This Z becomes the radius of the two sphere, the rho is the radius of the six spheres. There are some values for this axidilaton. The H3 form is 0, and the C2, so this C2 is like F3. It's actually constant because here it's in spherical coordinates, but if you put the Z squared in the omega 2 and you go to Cartesian coordinates, it becomes dx1 wedge, dx2 wedge, dx3 with just mu. So it's a constant C2 flux. So that would be the background in which we have the things. And to connect with the matrix model, the important thing will be, right, because the matrix model, it's discrete. We have those SU2 E-reps with the small ends, big ends, and we want to quantize things in gravity to identify. So, but because there are fluxes, the charges of those fluxes are quantized. It's like in electromagnetism. If you have magnetic and electric objects, then the product of the charges is 2 pi times an integer. And if something exists with g is equal to 1, then you have that the integral of those fluxes are integers. In supergravity, there is the same because there are all those gauge fields. The formula is a bit different because they have funny normalization. And the point is that the integral should be on a closed thing, on a closed manifold of the closed form. And you have those formulas that with those 3 forms, and also you can have a 9 form because you can take the Hodge dual of the axion. Those are integers. So we can do this analysis because, as I explained before, with those funny topologies, we have sigma 3 and sigma 7. I wrote here. We also have S9 because we go at infinity. We draw something of codimension 1. And we get that those integrals are integers. So here I gave some funny names to those integers, n-1 and d1 and ns5. That's because if you study in string theory what kind of objects have those charges, you find it's d1 branes, ns5 branes, and d instantons, so it's d-1 branes. So this integral of so this tilde, it's almost the Hodge dual. In spirit, it's the Hodge dual. It's just you have some modifications because the equations of motion cope with the different fluxes. But it's like the Hodge dual of the axion, which would be the gauge fields of this instanton. And so if you compute this integral, you find that it gives, right, F9 you can express explicitly in terms of V, and this V is expanded with multiples at infinity. In this size 9 we take very large, and you find it's a dipole. So the dipole is quantized. If you do around this sigma 7, so you go around the disk here, here you will find that it's the electric field that goes around, so you get the flux of the electric field, so you get the charge of each disk. So those charges are quantized, and also the distances with this sigma 3 here, you get the distance between them. All those quantities are quantized. And if you write the formula for the dipole, so P is Q times D, you will see that everything cancels, and you get back the partition of n. N is the sum of ns. Ns, if you do this identification, so big N, which was the size of the matrix, it corresponds to this number n-1, so the number of the instantons. The small ns, which was the multiplicity in the E-reps, it corresponds to nd1 to the charge. And this ns, it's the sum of all the distances, but then it's the height, right? If you're at that disk, you sum this distance, this distance, this distance, you get the height of that disk. So that corresponds to the size of the E-reps. So now we have this picture that I showed at the beginning. Those were the saddle points of the integral, and we can solve for this electrostatics. Right? You know those ends, those small ends and big ends, so you know where to put the disks and with which charge. Because you know the charge and the height, you can study the size they need to have such that the electric field vanishes. So it's a bit an implicit problem, but it can be solved in some specific examples. And you get this system, you can solve for V, you get V, you plug back, you get the gravity dual. So that's how the identification works in that case. Here we're just matching numbers, right? We say the number of AQR are the same as those geometries once you quantize the fluxes. But I will discuss something a bit more quantitative now. So before I showed the large N saddle point equation in the matrix model, and I would show that we can recover it from the gravity side. So you have to do something a bit funny. So you take what I was calling disk. It's three-dimensional ball because it's in a three-dimensional space. You can slice it, and this slice here, which now it's really a two-dimensional disk, it has a charge that depends on this u, and you write this charge f of u. So it's a bit arbitrary, but we'll see that this f is what connects to the eigenvalue density. It's not directly the full charge density of the disk. Now you have those balls, so you write what is the potential that is generated. So you know this f it's a bit equivalent to the charge density. It's like the derivative of the charge density multiplied by u is equal to this f. So you write the potential for that disk. It takes some integral form like that. So if you remember the integral from before, it's already start to look good. Here I just sorry, here it's the general potential, but now I evaluate the potential at the position of the disk. So at z is equal to zs, and the potential is constant if rho is smaller than this RT. So here you get some equation that the constant is equal to all those things, and how here I recopy the formula, and here it was the formula from before. When we did this large n saddle point, there was this μs, which was the Lagrange multiplier, which is equal to some term that is a square in the variable. Here, this z cube you can put on the other side because right, it's the height of the disk is a constant. Then you have those integrals, and you can see that the kernels are exactly the same. And in fact, you can match the quantities. So this x, which was the position in this StatMech picture, it get maps to rho. This rho, so the eigenvalue density get maps to this charge density of the disks here, and then you have a mapping of the constants also. So that tells you how to convert things in electrostatics to things in localization. Yeah, I don't know if you have questions about this. I will discuss some. So this is the first match we have, that those equations are the same. And now I will discuss something else. So if you have questions on this, maybe you can ask now. Great. So we'll talk about something else. We did not discuss too much what's the physics of those geometries, void geometries, but what is it usually? If you write Schwarzschild spacetime, you know it's a backreaction of a point mass at the origin. So here, what is it? There's something that is known from string theory. It comes from the non-abelian dBi action. Is if you take n d-1 branes and you put them in a constant Ramond-Ramond flux, then they will get polarized. Sorry, F3, they will get polarized into d1 branes. It's polarized because usually, right, the p branes, they couple to p plus 2, so they will couple naturally to F1, which is the action is like electrons are 0 branes and they couple to F2. And here we say if we put a F4, they could polarize. So electrons are not charged under F4. In the same way, the 1 minus 1 brane is not charged under F3, but if you put n of them, you have a polarization effect. It's like an atom, right? An atom, a neutral atom is uncharged, but if you put an electric field, then it polarizes because you have electron and a proton inside. So here it's the same kind of effect. And the original KKT model, you can think of it as the world volume theory of D-1 branes, and because it's the action that we thought is actually super Yang mills, but compactified down to 0 dimensions. And in the background that we studied, we found that asymptotically we have this constant 3-form flux. So that's the interpretation that those geometries, there are the back reaction of those polarized branes. So those are just words, but now we want to compute something to see this. So we can study the DPI action for D1 brane. So you put n the instantons, they polarize into a D1, and then you study this D1. You can take a spherical configuration. So you ask for everything to be spherically symmetric. So something that it depends only on R. Here it's you will have the it doesn't depend on those angular coordinates, and you find that this action simplifies to something here. And if you minimize that, so you look at what is, you have this spherical D1 and you minimize the action to find its radius, and you find this 3/8 something. But this actually matches the size of the fuzzy sphere. So this erupts. So there was this right race of x squared. You have some normalization if you do the mapping. This is the usual normalization when you map the matrices to the positions of the D branes. Just like this x, right? This xi that we found by minimizing the potential in the matrix model. You can take the trace of x squared, and you have those Yang mills. You use how it maps to those numbers, and you find exactly the same answer. And it also matches with something in the back reaction, which is the height of the disk. So you take the disk, you want to compute its height, so you integrate the metric, and it's again this 3/8 times the same factor. So that's the equation saying that probably this interpretation of polarized D brane is good. Now I will conclude. So we find those geometries that are in 1-to-1 correspondence with the saddle points of the integral, and there are instantons that polarize the D1 branes and back react into that flat space background. But this integral, it was right. We had this atomic picture where you have a gas with some interactions, and we know those two-body interactions. It was this plot attractive at resistance, then repulsive at short distance. You have those bound states. Why is it that this is well approximated by those geometries that actually are solutions to GR? So it's something that we would like to answer, and maybe more broadly would like to study this without explicitly using supersymmetry, because here with the localization we used supersymmetry a lot, but would like to still study the same model first, but without explicitly using it. So derive an effective action directly of the polarized IKKT in the small omega limit, and see if we can map with gravity there, because I mean at the end of the day we would like to understand outside of supersymmetry. So if we do this, supersymmetry will still be here, but it will not be manifest, and maybe some things might be more apparent. And also, it'd be nice to study a bit more the dictionary to really map the observables between the two. Thank you.
Okay, thanks very much, Antoine. So we have any questions?
Sorry.
I have one or two questions. First one is just to see if I got it right. The gravitational limit you said was when omega went to 0?
Yes.
Can you show again the equation?
So yeah, sorry, I quitted.
Yeah,
I'm in here.
yeah, exactly. So yeah, one should interpret then the SIKKT action as being equal to the purely gravitational action with nothing on it, and then the
Yeah.
deformation is turning on those.
So the limit should be taken after the partition function is an integral of this, and you take the limit outside the integral, and those things don't commute. So if you take the limit omega goes to 0, you don't get back IKKT observables.
And well, at least from my intuition, you're looking at saddle points, you're putting the fermions to 0, so you're looking at BPS saddle points of the quantum from the path integral in this dual model, and the path integral should be the same as the gravitational. So immediately the first thing that one imagines is, okay, you're looking for black brane solutions in supergravity. And so I was not surprised by your results, but the first thing that I thought was, well, what about the thermodynamics? You compute in terms of a gas, and are the thermodynamics of that gas related to the thermodynamics of the black brane solutions that you got?
Sorry, it's not black brane solutions, right? Those geometries.
The
But here
branes, they still have a horizon, right?
No, there's no horizon. It's smooth
There's no
everywhere.
horizon.
No.
The regular.
Yeah, it's regular everywhere in this rosy plane. So here you can write the blue lines. They are the conductors, so they are like boundaries, but you cannot cross them because it's boundary. But you can go around. You can go everywhere. It's always regular. There are no horizon, no singularity, nothing.
But then
I think you're thinking about the usual decoupling limit.
Yeah.
Which is a bit different here because the decoupling limit. So it's what people did at the beginning for pure IKKT, so without the mass deformation.
Yeah,
You
without
take decoupling limit and the instantons, and you have actually it's not yeah, you still don't have horizons because it's instantons. It's not really it's not yet brains. But if we look, it's the same for this BMN model, right? The BMN, if you take just this first line, it's the BFSS model that you can study by because it's the theory on D0 brains, and you can study the decoupling limit, and you have some geometry with black zero brains. But with this mass deformation, you have something that is closer to what we have. Is also there are no singularities, no horizons.
So does that tell you something about the thermodynamics of your gas?
No, I don't. Also, I mean, you right, if you want black holes, you typically do the gauge theory at finite temperature.
Yes.
Which you could do, for example, this BMN model, you put a finite temperature by compactifying time. But here, this right, it's more like static. You don't have a time integral, so it's not the same temperature.
Okay. I was thinking since you have a lot of particles and
Yeah, just the temperature of that gas is not the same as saying the time of the gauge theory, right?
yeah.
The compactifying.
Okay. So also when you have this theory, the polarized IKKT, and then you have that interpretation in terms of an electrostatic problem, right? So was that a natural? Is that like a very direct step to take when analyzing this model? Like how
So
that?
the electrostatics, it comes from gravity, right? It appeared because it was this gravitational solution depends only on some function that is harmonic.
Yeah.
So it's nice to use that trick of thinking about electrostatics where we have more intuition. It's easier to think of this electrostatics than to this, right? This is a hell. Well, this
Yeah.
electrostatics, you have the disks and it's easier to think. And we did not invent the trick. It was done in a few papers. Also in some BPS solutions in supergravity, you often have harmonic functions, and people have interpreted this in terms of electrostatics. So it's a different electrostatics each time, but it's a trick that is known.
Okay, so certain of these models, you expect to be able to play this game of thinking like an electrostatic problem,
Yeah,
right?
yeah. And here it's nice because we find in the matching that the charge density of the electrostatic problem matches with the density of eigenvalues. So
Yes.
it gives good intuition.
Yeah. Quite nice. Okay. Any more questions?
Yeah, Antoine, just maybe a stupid question, but can you also do something like this for BMN? Like consider these integrals and, or if not, what are the, why not?
Yeah. It was done for BMN. It's a paper by Asano. I don't remember the name, but I can send to you later.
Okay.
But they did almost the same. I mean, it was a great inspiration. This electrostatics, it was known by this paper by Maldacena and Lin. Then Asano did this localization and so has some partition function, and he derives some equation like this, and he matched that equation of the saddle points with the electrostatics of Lin Maldacena. So yeah, this I don't remember if you discussed, but yeah, you can totally do it.
Yeah. What's the interpretation in that case? Because in this it's I guess. Okay.
Yeah, it's the same. It's also some equation like that. Sorry, you say it's yeah, I don't remember if they have this gas interpretation. Yeah, I don't remember exactly the result. Because here the point for us was once we did this, it was to have this physical picture of an interacting gas, and those interactions are special because effectively they are described by gravity. So we did that step, but I don't remember if we did also.
Okay. Well, then there are no questions. Let's thank Antoine again. And we can end here. Thanks a lot.
Thank you.
Bye.